Welcome to The Explainer. Today, we're going to journey miles beneath our feet to uncover a force that's both incredibly powerful and completely invisible. Yeah, what does happen? It's a question with some seriously high-stakes answers. We're talking about immense energy and, well, a lot of potential danger. So let's dive right in. Okay, so before we get to the really wild stuff, we've got to set the stage. We need to figure out what normal even looks like, way deep underground. All right, this is the big one, the fundamental concept. I want you to picture a rock, any rock, but miles underground. It's not a solid block, right? It's more like a super dense sponge. It has all these tiny, tiny open spaces. We call them pores, and they're all filled with some kind of fluid. And that fluid isn't just chilling in there, it's under constant squeezing pressure from every direction. So this is our baseline, what geologists would call hydrostatic pressure. Think of it this way. If all those tiny pores in the rock are connected in a continuous chain all the way back up to the surface, the pressure just builds up nice and steady the deeper you go. It's really just the weight of that column of water pushing down, kind of like the pressure you'd feel at the bottom of a really, really, really deep swimming pool. This is our normal, predictable state of affairs. Okay, but normal is only half the story. The really interesting part is what happens when that nice, predictable system gets broken and the pressure goes completely off the rails. Let's take a look at a real-world example from the Texas Gulf Coast. This data is from a place called the Monte Cristo Field, and it's a textbook case. Imagine you're the one drilling this well. For the first 8,000 feet or so, everything is going exactly as planned. The pressure is increasing at that nice, steady, predictable rate, that straight line. It's all good because it means you're in an open, connected system. And then, boom, everything changes. Just look at where that line goes. Suddenly, the pressure readings take a hard right turn and start climbing at a frankly terrifying rate. That's the dead giveaway. That's the signal that the fluid down there is no longer connected to the surface. It's trapped. It's sealed inside what's basically a high-pressure bomb waiting to go off. So how bad is it? The pressure increase jumps to 3.7 psi for every single foot you drill down. Now, to put that into perspective, that is more than 8 times the normal rate. 8 times! The pressure from the fluid is building so much, it's actually starting to push back against the weight of all the rock above it. It's literally holding up the mountain. This is what geologists call hard overpressure, and believe me, it is every bit as dangerous as it sounds. Okay, so how does this even happen? What's creating these isolated pressure pockets? Well, the answer isn't in the fluid itself, it's in the plumbing, the structure of the underground. And here's the key idea you have to get your head around. The underground isn't one big uniform sponge. It's more like a maze of sealed-off rooms. You've got these geologic faults and layers of rock that just don't let fluid pass through. We call them impermeable. They act like walls, floors, and ceilings, creating these things called reservoir compartments. And the crazy part is, each one of these rooms can have its own completely unique pressure, totally sealed off from the room right next to it. This is a fantastic example. It's a real tale of 2 fault blocks. Down in a field called South Eugene Island, you have 2 sections of the exact same sandy rock. They are literally next-door neighbors, but they're separated by a fault. And just look at the difference. Block A, super high water pressure, a little bit of oil. But right next door, in Block B, you've got lower pressure, but a huge amount of natural gas. That fault is a perfect seal, creating 2 totally different worlds just feet from each other. You can imagine the stakes here, right? Drilling into the wrong one could be an absolutely massive, multi-million-dollar mistake. And you can see this another way, too, just by watching how these fields behave over time. Take a look at Sand 1. When they started producing from it, the pressure dropped evenly across the whole thing, just like you're draining one big fish tank. Easy. But then you look at Sand 2. It was a real head-scratcher. They'd drain one well, then they'd go drill another one just a little ways away, and whoa, the pressure was back up to the original, undrained level. That's the clue right there. It tells you that Sand 2 isn't one big room. It's secretly divided up by a bunch of smaller, invisible walls into a whole series of little sealed pockets. Okay, so we get it. These sealed-off rooms exist. But what's actually pumping them up? What's the source of all this crazy pressure? Let's get into the mechanics of it. Right, so it turns out there are a few different ways this can happen. You've got tectonic plates squeezing things, you've got weird chemical reactions, all sorts of stuff. But for a lot of the big resource-rich areas in the world, like, say, the Gulf of Mexico, there's one cause that's considered the main culprit. And that main culprit is something called disequilibrium compaction. I know, it's a mouthful. but the concept is pretty simple. Just picture mud and sand getting dumped on the seafloor and piling up super, super fast. As those layers get buried deeper and deeper, the crushing weight of everything on top tries to squeeze the water out of those little pores. Now, normally, the water would just squish out and escape upwards. But what if it gets trapped under a really dense, watertight layer, like a thick shale? Well, then it has nowhere to go, and it's exactly like squeezing a water balloon that has no opening. The water itself has to support all that weight, and the pressure just skyrockets to absolutely insane levels. So, this all leads to a really big, multi-billion-dollar question for the engineers and geologists who are trying to drill into these areas, right? How in the world do you map out a deadly pressure zone that's totally invisible and buried miles under the ground? I mean, you can't just drill a bunch of test holes. That's way too dangerous and expensive. The answer, it turns out, isn't about what you can see, but what you can hear. It's honestly a brilliant piece of detective work. It works in 3 steps. Step 1, the principle. Remember how that high-pressure fluid is holding up the rock? Well, that means the rock is actually less squished together. It's more porous and kind of fluffier than it should be for that depth. Step 2, the physics. We send sound waves down there with seismic surveys, and it turns out sound travels slower through that fluffier, less compact rock. So step 3, the result. We can map out the areas where the sound waves are moving unusually slow. And voila, we've just created a map of the hidden high-pressure zones without ever having to touch them. And this is what you get at the end of the day. You transform all that abstract seismic data, which honestly just looks like a bunch of squiggly lines on a screen, into a practical, color-coded pressure map. It's like a treasure map and a danger map, all in one. It lets drillers aim for the good stuff while steering clear of a catastrophic blowout. It literally turns a huge, terrifying risk into something you can actually manage. All right, so we've taken a deep dive into the Earth's pressure cooker. What are the big takeaways here? What's the why this matters part? Well, first and foremost, it's about safety. Being able to predict these overpressure zones is absolutely critical to preventing blowouts when drilling. Second, it's about efficiency. You have to know if you're tapping into one giant reservoir or a dozen tiny separate pockets. That completely changes your strategy and, your budget. And finally, it's just fundamental geology. This invisible force of pore pressure is a key player in shaping the subsurface, influencing everything from how strong a rock is to when a fault might decide to slip. And that leaves us with a final big question. As we keep pushing to find resources in deeper and more complicated parts of the world, how are we going to keep up? How will our ability to predict these hidden pressures evolve? It's a massive challenge, constantly pushing the limits of what we know about geology and physics. And it's a great reminder that no matter how well we think we know our planet's surface, there are still some incredible, powerful secrets waiting to be unlocked miles and miles beneath our feet.